In this video, I'm talking about alternating series error bound. And so this would go with the alternating series video. I just didn't have enough time to include error bound examples in class. So here I am. I'm going to talk a little bit about error bound. And so we're going to start with going back to that example, the alternating harmonic series. And what we had done was we had, added up some of the partial sums. We'd kind of drawn a diagram, and we saw that it was looking like it was going to converge onto some number, about there. Okay, and so see, I've listed out S5, and I think I actually did 6 terms. I added up 6 terms because I see that S6 right there in the original video, but I think it got erased or something. So what I'm going to do is I'll just get rid of the 6th term, and I'll say, okay, talking about the error, okay, the difference between our approximated value, okay, so the difference between 0.783 and the true value of the conversion series. Well, the true value of the error would be this distance here, right? The distance between S5 and whatever it's converging to. So we'll call that the error. Hey, but we don't really have a way of knowing the true value of the error. And if we did, then we wouldn't even be that interested because we would know what the series actually converged to. Okay, so that would kind of, ruin the whole point. What I'm going to do instead is I'm going to try to, get some sort of upper bound for the error. Something that's definitely bigger than the error, so I could, put a certain range on what this series converges to. And what would serve as a decent error bound for S5 would be that 6th term that I added in, right? Okay, when I add that in, this distance is certainly bigger than the error. Always. That next term. And so that's what we're going to say. That the error, when we approximate the value of a convergent alternating series with, a certain number of terms, that error is no larger than the first neglected term. Okay, so another way of saying this would be that, your error is smaller than the next term, or at least the absolute value of the next term. Or that, the difference between S infinity and the nth partial sum, it is definitely no more than the absolute value of a sub n plus 1. This is the alternating series error bound. So I'm going to go back up a second. So going back to this example of the alternating harmonic series, the difference between the partial sum of adding up 5 terms and the true value is no more than the 6th term. Okay, well, I know what a sub 6 is. A sub 6 equals, negative 1/6. So I can conclude that the difference between, the true value of this infinite series over n, the difference between this and 0.783 is less than 1/6. Okay, I know it's less because of the diagram and how this series is going. In general, you say it's less than 3. All right, now for some other examples. All right, so here we've got 1984 BC number 4. And it's defining this function f of x in terms of some sort of infinite series. And this infinite series has got objects that we have not seen yet. It's got an n factorial, it's got an n to the n, and at first I was considering not including this in the examples today, but I actually do like it because it kind of goes to show you that it doesn't really matter as far as the error bound goes, what kind of crazy stuff you've got in your series. So the first prompt, in part A, it says find the radius of convergence of this series. We don't know how to do that yet, okay? Once we do, that'll be in the ratio test video, okay, finding the radius and interval of convergence. Okay, we're not going to do that. Okay, part B says use the first 3 terms of the series to approximate f of negative 1. All right, we can do that. That's just kind of a plug into the formula and see what's going to happen. All right, well, that means if f of x is the sum from 1 to infinity of x to the n times n to the n divided by 3 to the n times n factorial, And that means that f of negative 1 will equal the sum from 1 to infinity of negative 1 to the n. Okay, so that makes it an alternating series. N to the n over 3 to the n factorial. It's got a lot of stuff going on. So what we're going to do is we're going to just start writing out some terms. Okay, so this would be equal to, starting at 1, okay, negative 1 to the 1 is negative 1. N is 1, 1 to the first power is 1, so that's 1 in the numerator, divided by 3 times 1 factorial. Okay, plus, right, negative 1 to the 2 power is positive 1, 2 to the 2 is 4, and then divide by 3 to the 2 and 2 factorial. You could simplify this if you felt like it, but you don't have to. And then I'm going to add, okay, when n is 3, I want the first 3 terms. Okay, so that's going to be negative 1 to the 3 is negative 1. And 3 to the 3 is 27. Divided by 3 to the third is 27 times 3 factorial is 6. Okay, that is an approximation for f of negative 1. If you really felt like you had to, you could probably reduce this thing, but, you know, or you could just not. I really would recommend not. It looks like you're going to have that common denominator of, like, 18 or something. I guess it wouldn't be too hard, but what's the point? You know, you're just risking an arithmetic error. Okay, so part C says estimate the amount of error involved in the approximation from part B. Justify your answer. All right, well, I know that the error is less than or equal to the absolute value of the next term, the first neglected term. Well, I used 3, so the next one would be the fourth term. Okay, so it's going to be less than or equal to, that's where n is 4. So negative 1 to the 4 is positive 1. 4 to the 4, I don't even know what that is. I think that might be 256, but I'm not sure. I mean, it doesn't even really matter. 3 to the 4, and 4 factorial. Okay, that's a solid error bound. That's all they're looking for on that. They're just looking for you to know that the error is bounded from above by the next term, and for you to know what the next term means. Okay, if you use 3 terms to approximate, then the error bound is just the value of the fourth term. Okay, and the last example I've got for you is kind of the backwards question of, you know, how many terms of this series do I need to take to approximate the true value of the infinite sum with error less than some value, in this case 0.01, which is 1. Okay, well, what we know is that we know that the error is bounded from above by the absolute value of the next term. That doesn't really help us here. What does next term even really mean? Well, if we're going to use n terms to approximate, then the next term would be a sub n plus 1. So I'm going to actually label it with a sub n plus 1. And we need that to be less than 0.01. So I'm actually going to say that now I need a sub n plus 1 to be less than 0.01. But I have a fraction here, and so I'm going to change that some n's are given as fractions, so I'm going to change this to a fraction as well. It might be a little easier to compare. Okay, well, the n plus first term, oh, I see that I don't have an index up here. I'm just saying n plus 1. But the absolute value of a sub n plus 1 will kind of make that irrelevant. And so what I'm going to do is I'm going to say the absolute value of a sub n plus 1 is going to be 4 over n plus 1 squared, being less than 1 over 100. Right? Well, I think what I might do is I might just kind of divide both sides by 4. That will preserve the direction of the inequality. So I've got 1 over n plus 1 squared is less than 1 over 400. All right, and if this fraction is less, it means that the denominator has to be bigger. That's a little tricky right there. I mean, that's slightly subtle. So I'm going to need n plus 1 squared to be bigger than 400 in order for that to happen. Okay, so the n plus 1 squared needs to be greater than 400. Now, n is going to be strictly positive because it's the index of a series, so I'm not going to worry about the plus minus here. I'm going to say n plus 1 needs to be greater than 20, so n needs to be greater than 19. Okay, the first one that's greater than 19 is 20 terms, so I need 20 terms. In order to approximate the true value of the infinite series within 0.01 of the actual value. And that's all I got for you on alternating series error bound.